Imagine yourself sitting beside a large window on a pitch-black night, with stars twinkling like millions of tiny lamps suspended in the vast black sky, and a gentle wind whispering through the treetops outside, carrying a crisp chill that makes you shiver in delightful anticipation. You take a deep breath, feeling the fresh air fill your lungs, and then your mind begins to wander toward the most wondrous aspects of the universe. We have all heard about the Big Bang, that colossal moment marking the beginning of time and space, like an enormous explosion echoing from nothingness, creating everything around us from the sparkling stars to the lush green planet we call home. But pause for a moment, breathe even deeper, and ask yourself this question: what if the birth of our universe was even more extraordinary, more miraculous and unexpected than anything we have ever imagined? Let me share with you a different story, one that will make your heart beat faster with curiosity and awe, as if you are lost in a science fiction dream yet grounded entirely in the solid foundations of physics. Instead of emerging from a chaotic explosion, our universe might have been spewed forth from a white hole, a concept that sounds unfamiliar but brimming with allure, like a gigantic cosmic fountain where matter and energy surge outward rather than being devoured. Picture the scene: a brilliant region of space where light and fundamental particles burst forth like dazzling fireworks on New Year's Eve, giving rise to countless stars, planets, and even the very life we experience. This idea remains purely theoretical, existing only in complex equations and the speculations of scientists, but it opens up an exciting twist, compelling us to revisit the entire narrative of the universe with wider, more inspired eyes. In fact, as of 2025, ongoing research including advanced computer simulations and indirect observations from telescopes like the James Webb Space Telescope continues to explore these possibilities, hinting at subtle clues in the early universe that might align with such a dramatic origin story. Now, let us delve deeper into this realm together, as if strolling along a winding forest path where each step uncovers a new secret. First, we must understand what a white hole truly is by contrasting it with its opposite counterpart, the black hole. A black hole resembles a colossal cosmic vacuum cleaner, a dark and terrifying expanse of space where gravity is so intense that it engulfs everything nearby, from shimmering cosmic dust to blazing stars, and even light itself cannot escape. Envision standing near a black hole. The air around seems heavier, sounds distort unnaturally, and all things are dragged inexorably toward the center like leaves caught in a swirling whirlpool. The boundary of a black hole is known as the event horizon, an invisible threshold where, once crossed, there is no turning back, only a plunge into eternal darkness. Recent observations in 2025, such as those from the James Webb Space Telescope, have revealed supermassive black holes in surprisingly tiny early galaxies, challenging our understanding of how these monsters formed so quickly after the Big Bang, and providing fresh data on their event horizons through gravitational lensing effects. In contrast, a white hole is the perfect inversion, like a painting flipped upside down under the sun's warm glow. Rather than devouring, it ejects matter and energy like a radiant cosmic fountain, where fundamental particles fly outward at dizzying speeds, fostering life and illumination. The event horizon of a white hole exists as well, but here, you can only exit, never enter. Imagine the interior of a white hole as an immense tunnel, yet instead of stretching endlessly and consuming, it contracts and opens wide, releasing everything into the expansive universe. Both entities, black holes and white holes, emerge as solutions from the same set of equations crafted by Albert Einstein in his general theory of relativity, those profound equations describing how space and time curve under the influence of gravity. The general theory of relativity, unveiled by Einstein in 1915, revolutionized our view of the cosmos, and even in 2025, it remains the cornerstone for most cosmological models, though it is increasingly augmented by quantum theory developments. The formation of black holes typically begins with the gravitational collapse of a massive star. Picture a star dozens of times larger than our Sun, burning brightly in the frigid void of space, emitting warm light that illuminates surrounding planets. When its fuel depletes, the star contracts under its own immense weight, gravity crushing everything into a singularity, a point of infinite density where ordinary physical laws break down. The result is a black hole, encircled by an event horizon like a shell of impenetrable shadow. But what of white holes? They arise from those very same equations, albeit with a reversal of time, like watching a film of a black hole played backward. Instead of absorbing, they expel, functioning as origins rather than sinks within the fabric of the universe. Theoretical physicists in 2025 are using supercomputers to model these time reversals, incorporating data from gravitational wave detectors like LIGO, which have detected dozens of black hole mergers since 2015, indirectly supporting the mathematical symmetry between these cosmic twins. A physicist named Carlo Rovelli, whom we might envision as a passionate Italian man with eyes alight when discussing the cosmos, seated in an office overflowing with books and chalkboards scrawled with formulas, has proposed a fascinating idea. A black hole could transform into a white hole under a crucial condition, namely that it must be exceptionally small. Rovelli, a leading theorist in loop quantum gravity, a framework attempting to reconcile general relativity with quantum mechanics, has developed this concept over years of dedicated research. Feel the thrill in considering this. Most black holes we observe in the universe are enormous, such as the supermassive ones at galactic centers weighing millions to billions of times the Sun's mass, making such a transition energetically improbable. Yet Rovelli introduces a new layer of intricacy by incorporating quantum leaps, a phenomenon from quantum mechanics where the black hole abruptly shifts to a white hole state. In his 2023 book titled White Holes, Rovelli elaborates on this journey into the hearts of black holes, where space and time dissolve, and a white hole emerges, drawing parallels to Dante's Inferno for poetic depth. By 2025, this theory sparked debates, including a notable head-to-head discussion with Roger Penrose, where they explored whether white holes challenge Einstein's general relativity, with Penrose advocating for cyclic cosmologies that might incorporate similar bounces. To grasp this more fully, consider quantum mechanics as a bizarre realm where events unfold by probability rather than certainty. When applying quantum gravity, the fusion of relativity and quantum mechanics, a field burgeoning in 2025 with models like string theory and loop quantum gravity, we calculate that the probability of this leap is nearly zero for large black holes. From an external viewpoint, it is utterly negligible. But for a small black hole, the odds skyrocket. And how does a black hole become small? Through the process of Hawking evaporation, proposed by Stephen Hawking in 1974. Black holes are not eternal. They emit radiation akin to a hot object, gradually losing energy and shrinking over time. Envision a black hole as a glowing ember cooling in the icy expanse of space, emitting faint glimmers and dwindling progressively. Detailed simulations in 2025 confirm that this evaporation rate accelerates dramatically for smaller masses, with microscopic black holes potentially exploding in bursts of energy, though no such events have been detected yet. If you wait long enough, truly long, far exceeding the current age of the universe, even the colossal black holes from massive stars or supermassive ones with masses billions of times that of the Sun will shrink to minuscule sizes. Once diminutive, the quantum leap probability becomes virtually assured, and suddenly it transforms into a white hole. This narrative aligns with astrophysical physics. Every black hole will eventually evaporate per Hawking's calculations, leap, and become a white hole. Inside the white hole, space expands vastly, but it takes an immense duration for contents to fully emerge. Recent theoretical work, including a 2025 paper on stimulated emission of radiation preserving black hole information, suggests that during evaporation, quantum effects could encode the hole's history in the outgoing particles, adding credence to such transformations. Now, let us discuss time, a notion that induces vertigo due to its peculiar disparities. For a black hole like Sagittarius A star at the heart of our Milky Way galaxy, a behemoth approximately 4 million times the Sun's mass, first detected via radio signals in the 1930s by Carl Jansky and confirmed as a black hole through decades of study, with the inaugural image from the Event Horizon Telescope in 2019, the evaporation timescale exceeds the universe's current age of about 13.8 billion years, potentially stretching to quintillions of years. Yet inside the black hole, time flows differently owing to relativistic time dilation. Imagine yourself as a brave astronaut aboard a spacecraft like Starship, hurtling toward the black hole without being crushed, a mere supposition, as tidal forces would actually tear you apart. From crossing the event horizon, the journey to the leap spans mere minutes, or even seconds for large black holes. The leap occurs instantaneously, and emergence from the white hole takes only minutes more. Externally, billions of years pass like a prolonged sigh. Internally, just seconds or minutes elapse. This discrepancy renders the universe akin to a book with shuffled temporal pages, brimming with enigma and adventure. In 2025, the James Webb Space Telescope captured images of a naked black hole 50 million solar masses heavy in the early universe, rewriting formation timelines and amplifying these temporal puzzles. The white hole concept is profoundly captivating, quickening your pulse with its potential, yet it lingers as advanced theory. They have never been directly observed, and their existence contests our grasp of entropy, the inexorable increase of disorder over time, and the arrow's direction toward the future. Entropy, per the second law of thermodynamics, invariably rises, but white holes appear to reverse this. Nevertheless, theorists like Rovelli persist in speculating on their cosmic role. If Rovelli's idea holds, white holes might resolve Hawking's black hole information paradox. A major conference in November 2025 marked 50 years since the paradox's inception, gathering experts to debate resolutions, with emerging consensus that information escapes via Hawking radiation, though mechanisms remain contentious. Allow me to elaborate on this paradox, as if seated by a campfire recounting a scientific ghost story. Hawking initially believed that hurling information into a black hole, a hard drive, a hefty tome brimming with invaluable knowledge, or any object would destroy it at the singularity, where time ceases. Picture the book soaring into obscurity, pages dissolving, knowledge lost forever. But Hawking then discovered black holes radiate, possess temperature, and evaporate gradually. If the black hole vanishes, whither the information? If destroyed, the universe loses determinism. We cannot predict futures from pasts, violating science's core tenet that information is conserved, neither created nor annihilated. For decades, Hawking and peers pondered information destruction, posing profound issues. Yet from the 2010s through 2025, most physicists concur that information endures, emerging in Hawking radiation, albeit the precise method sparks debate. Ideas like wormholes linking black hole interiors to distant universes, or the holographic principle, information stored on the event horizon like a three-dimensional hologram from two-dimensional data, pioneered by Gerard T. Hooft and Leonard Susskind in the 1990s, have advanced. By 2025, quantum models such as the anti-de Sitter conformal field theory correspondence bolster that black hole interiors may not exist independently, with everything encoded on the surface. A 2025 hypothesis posits spacetime itself as a quantum memory matrix, storing information holographically and offering fresh insight into preservation during evaporation. The holographic principle, chiefly tied to black holes, unlocks possibilities for universal genesis. If information conserves in black holes, perhaps our universe sprang from an analogous white hole. This line of thought posits origins not as a simple Big Bang singularity, but from a white hole. Rovelli's black hole to white hole theory, intertwined with the information paradox and holography, furnishes a novel lens for viewing cosmic birth and evolution. Notably, Rovelli's framework rests on robust theoretical physics, sparking immense interest, yet remains speculative, fueling ongoing 2025 debates via simulations and James Webb Space Telescope hunts for indirect signatures like anomalous early universe emissions. History instructs patience in science. Black holes were once doubted. In the 1970s, some astronomers noted Doppler dancing stars suggesting invisible companions, possibly black holes, but the community dismissed it lightly. Then in the 1930s, Carl Jansky erected an antenna capturing radio signals from Sagittarius core, dubbed Sagittarius A star, the first earthly black hole signal. It took half a century for confirmation. Similarly, white holes may await their vindication. We comprehend quantum mechanics, general relativity, Black hole behaviors. Flipping perspectives, inserting white holes, might yield coherent narratives. Future experiments, perhaps from next-generation telescopes or particle accelerators, will discern truth from fancy. As we probe this possibility, white holes compel rethinking all we know of the universe. They serve as thrilling reminders of vast unknowns, igniting imagination and stretching science's boundaries. This pursuit, driven by wonder, the awe of beholding the night sky, heart swelling with hope and rigorous inquiry, keeps cosmic discovery vibrant and enthralling. In 2025, James Webb Space Telescope's glimpses of primordial black holes and super Eddington accretors 1.5 billion years post-Big Bang further fuel these quests, revealing black holes devouring stars in dusty galaxies and hinting at direct collapse formations without stellar precursors. Whether white holes exist or not, they symbolize humanity's ceaseless quest to explore, illuminating the universe's spectacular mysteries. And who knows, perhaps one day, as you sit again by that window on a whispering night, you will smile knowing the cosmos is more extraordinary than ever before.